Okay, sorry. I think we are ready. There was some technical problem. Uh, can you see the screen? Daria?
Yes, sir.
Okay, thank you. So we were talking about three important problems in the security of hash function. Pre-image resistant. So we want our hash function to be pre-image resistant. Okay. We also want our hash function to be second pre-image resistant, and we also want our hash function to be collision resistant. As I mentioned, so collision resistance will imply in certain specific conditions, second pre-image resistance and pre-image resistant. Okay. Now we looked at the random oracle model and looked at the ideal function of H. Okay. So in random oracle model, a hash function is chosen randomly from this set, and we are only permitted oracle access to the function H. Okay. The only way to compute Hx is to query the oracle. So this was the important result, that suppose H is a hash function chosen randomly and x naught is a subset of x, and suppose size of y is m. Suppose that the value Hx have been determined by querying the oracle if and only if x is in x naught. Okay, then probability that Hx is equal to y, this is a conditional probability, is actually 1 by m for every x in x/x naught, and also y is in y. So this result we have used earlier, and will be using it today also. Okay. Algorithms in random oracle model. The algorithm is said to be randomized algorithm if they can make random choice during their execution. A Las Vegas algo is a randomized algorithm that may fail to give an answer, but if algo does return an answer, then answer must be correct. Then that is known as Las Vegas algo. A randomized algorithm has worst case success probability epsilon if for every problem instance the algorithm returns a correct answer with probability at least epsilon. Okay. And a randomized algorithm has average case success probability epsilon if the algorithm returns correct answer average over all problem instances of a specified size is at least epsilon. Okay. So these two things we defined. We talked about epsilon q algo. These denotes a Las Vegas algorithm with average case success probability epsilon, in which the number of oracle queries made by the algorithm is at most q. Okay. So we looked at find pre-image algorithm, and we saw the following result: that for any x not in a subset of x, and if the size of x naught is q, the average case success probability of algorithm 5.1 is epsilon is equal to 1 minus 1 minus 1 by m raised to power q. Okay, we proved it using theorem 5.1. Similarly, we look at find second pre-image algorithm and we analyze it, and the result was this theorem: for any x naught subset of x minus x with size of q naught x, with size of x naught is q minus 1, the success probability of algorithm 5.2 is this. Okay. Finally, I would like to mention the last algorithm, which is collision. This is an important one actually. Let me. So we call it as Algo 5.3 find collision. H comma Q is the input. Okay. So choose x naught as a subset of x, and size of x naught is equal to q. For each x in x naught, okay, what you do, assign hx as yx if yx is equal to yx prime for some x distinct from x prime. Okay, then return the pair. Means collision is found, right? Else return failure. Okay, so this is the collision algorithm. So actually, there is a analogy of this analysis of this algorithm with uh, probability argument of birthday paradox. So let me mention what is birthday paradox, and then we will discuss this. Birthday paradox. Okay, birthday paradox says that in a group of 23, remember the number, 23 randomly chosen people, at least 2 will share a birthday. It's very interesting problem with probability more than half. If you choose a group of 23 randomly chosen people, okay, uh, at least 2 will share a birthday with probability greater than half. So now you can see that we can formulate this as a hash function problem, collision, with respect to hash. So since if we define h, suppose domain, if you look at the domain of the function as set of all living human, okay, and for every x in this domain, suppose hx, our hash function is the birthday of a person x. Okay, the range of h will be 365 days, right? Actually, if February is 29, so in that case 366 days, otherwise 365 days. Now finding 2 people with the same birthday, okay, finding 2 people with the same birthday is basically finding a collision of this hash function hx, right? So birthday paradox basically says that algo 5.3 that we discussed, as per the birthday paradox, this says that algo 5.3 has success probability half when q is equal to 23 and m is equal to 365. Okay, so there is a this algorithm 5.3, will have success probability half. Okay, now I think I can mention the following theorem. For any x naught subset of x with size of x naught is equal to q. Okay, the success probability I can compute of algo 5.3 is epsilon is equal to 1 minus m minus 1 by m minus 2 by m minus q plus 1 by m. Okay, So let me give you a very quick proof of this fact, and then we can analyze this algorithm, this theorem. Proof: suppose x naught having q points, x1, x2, xq, okay, and suppose for 1 less than equal to I less than equal to q, for each I like this, ei be the event that hxi does not belong to hx1 hxi minus 1. Okay, if this is the event, observe that probability of E1 is 1. Using induction, it follows from theorem 5.1, which we just discussed, that probability of EI condition E1 and EI minus 1 will be m minus I plus 1 divided by m, or 2 less than or equal to I less than or equal to q. Okay, so therefore the probability of E1, okay, E1 up to EQ is equal to m minus 1 divided by m minus 2 divided by m minus q plus 1 divided by m. Okay, so that means the probability that there is one collision at least one collision is 1 minus this quantity E1 and EQ. So the probability of finding no collision is what? Of finding no collision is, I can simplify 1 minus 1 by m, 1 minus 2 by m, up to 1 minus q minus 1 divided by m, which is nothing but partial product 1 minus I by m, I is equal to 1 to q minus 1. Okay, now note that e raised to power minus x is nothing but 1 minus x plus x square by factorial 2 minus x cube by factorial 3 and so on. Because of this, if we take first two terms, we can get an approximation that for small values of x, e raised to power minus x is same thing as 1 minus x. Okay, this formula I can use it here. So this probability will be equivalent to partial product I is equal to 1 to q minus 1 e raised to power minus I by m, right, which is nothing but e raised to power minus summation I is equal to 1 to q minus 1 I by m. Okay, this I can sum it. This is e raised to power minus q times q minus 1 divided by 2m. So therefore probability of finding one collision will be 1 minus e raised to power minus q times q minus 1 divided by 2m. Okay, if you call it epsilon, okay, so then I can solve. Actually, then if epsilon is equal to this quantity, I can solve for q actually. So this implies that, so if epsilon is equal to 1 minus e raised to power minus q times q minus 1 divided by 2m, this implies that e raised to power minus q times q minus 1 divided by 2m is equal to or equivalent to 1 minus epsilon, right? That means minus q times q minus 1 times 2m is equivalent to log of 1 minus epsilon. I can take log on both sides. This implies that q square minus q equivalent to 2 times m log of 1 minus epsilon. Okay. I have ignored minus q actually. So basically ignoring minus q will give us q as equivalent to 2m log of 1 over 1 minus epsilon. If we take epsilon is equal to 0.5, q turns out to be 1.17 times square root of m. That means hashing such over square root of m random elements of x yields a collision with probability of 50%. That means hashing just over square root of m random elements of x yields a collision with a probability 50%. Probability of 50%. Okay. So basically, if m is equal to 365, the birthday paradox kind of thing, if we do, q will be 22.3. Therefore, probability will be is greater than half. Okay. So actually, this problem tells me how to find collision with what probability, the success probability of collision. Okay. So actually, there is a lower bound on the size of the pure message digest, right? So what if 40-bit message digest means the value of hx. A 40-bit message digest would be insecure. Since a collision will be found with probability half. Okay, which is just over 2 raised to power 20 million random hashes. It's about a million. Okay. Okay. So basically, our popular algorithm SHA1 has message digest 160 bits. So basically, this birthday paradox sets a lower bound of what should be the size of the message digest. So birthday attack will require in this case 2 raised for 80 hashes in this case. Okay, to find a collision. Okay. So this is a interesting analysis anyway. Now I guess I can tell you about iterated hash function. Okay. So I just want to mention one thing that if we compare the security criteria for hash function, we need to keep this thing in mind that collision resistance will imply pre-image resistance and second pre-image resistance. Of course, under some specific circumstances, under some assumptions. Okay, so that means we are going to focus on collision resistance if you want to check any hash function. Okay, so now I think we are ready to describe you the procedure. So I'm going to tell you SHA3, how to construct SHA3, which is a popular hash function. But before that, I need to give you a general construction method. And in fact, of the iterated hash functions, how they are constructed, a general method. So I should say, now I'm going to talk about a general method for construction of iterated hash function. Okay, what is the general method for the construction of iterated hash function? So here H will have infinite domain. Okay, this is something to keep in mind. Another thing that we are going to focus, that input and output of H are binary strings. Okay, so input output are binary strings. We denote length of X by this symbol, length of a string X. It's a binary string anyway. If X and Y are two binary strings of some length, I'm not worrying about, so that's why I put a star. Then X concatenation Y is concatenation of X and Y. Right, we are combining these two strings. I mean, side by side, we are putting them. Okay, so these are some just basic, things. Now let me give you the general construction. So we are going to use a compress function. What is compress function? Let me give you. So compress function. Compress function, or compress is a function from m plus t size to m bit. So m plus t is the input size and m bits are the output size. Essentially, you are reducing the bits, right? That's why it is known as compress function. Okay, you are making m plus t bits to m bits. This is known as compress function. T is greater than or equal to 1. Okay, so we can construct a iterated hash function H from union of I is equal to 1, sorry, m plus t plus 1 to infinity 0 1 raised to power I going to 0 1 raised to L. Okay, based on compress function, compress. This is a compress function which is compressing m plus t bits into m bits. Okay, so there are a couple of steps. So let me tell you. Step number 1 is pre-processing step. So what we are doing actually now, we are actually telling you how to construct a hash function. Okay, a general procedure of iterated hash function. So given a input string X, the size of X is at least m plus t plus 1. Okay, construct a string Y. Y using a public algorithm such that length of Y is multiple of t. Okay, length of Y is multiple of t. Remember, using a public algorithm. So input string is X, construct a string y, which is kind of an output string, using a public algorithm such that the length is multiple of t. Okay, then we can think of y as, we denote y as y1 concatenation y2, and like this concatenation yr, where each yi size is t, or 1 less than equal to I less than equal to r. In this case, obviously, it will be a multiple of t, right? So step 1 is input string is of length m plus t plus 1, because see, it is going from here. Input string is of length at least m plus t plus 1 or more. Output string has length multiple of t, pre-processing step. Okay, so normally this is done by paddings. Let me explain to you what is that mean, but anyway, step 2 is processing step. What you do, let iv is the initial value, public initial value. That is a bit string of length m. Okay, then you compute z0 as the initial value, z1 as a apply compress function on z0 and y1. Remember, y1 is of size t. What is the z0? Size m, right? So m plus t, right? So that goes into m z1. So you're compressing this into z1, which is again a string of length m. Okay, z2 using compress function, y2, and so on, zr compress function, zr minus 1, yr. So basically, how do we do this step by step? Let me show you a picture here. Here is the picture. So you see that initial value, public initial value is going here, then y1, and then compressing this goes to z1, then again concatenated with y2, right? Then compress goes to z2, concatenated with y3, again compress, and like this you keep on doing. Finally, output is zr. So this, because of this picture, it is known as iterated hash function. Okay. Finally, step 3 actually. Step 3 is basically output transformation. This is an optional step. Okay. So G is a function from M bit string to L bit string. It's a public function. So we define h of x. Our hash function is g of zr. Whatever zr is coming from this iteration, this zr, we are actually taking g of zr is equal to h of x, our hash function. This is the output. If the output function g is not used, h of x is simply zr, If g is not used, then h of x is simply zr. Okay. Okay. Huh? So now, okay. Now, what is a common way to construct a string in step 1? String y in step 1. Here in step 1, the common way to construct a string is basically you take x and pad it using some pad function. Normally we pad it with zeros, additional bits such as 0. Okay, padding function. Therefore, now size of y is multiple of p. Remember what was the size of x? Was this. Okay, so we are adding additional things such that it is a multiple of p. So the pre-processing step must ensure that the mapping this, x going to y is injective mapping. Otherwise, as you know, if it is not injective, there will be a collision. It will not be a collision resistant. So this is a important condition that we need to have. Now I think so. This was the general procedure, general method. Now I'll give you a specific construction. Okay, which is known as Merkel Damgard construction. This is an important construction method, and that is used in variety of algorithms. So again, I just recall. So in this general method, you need to have a pre-processing step where you are padding. Okay, then you have processing step where you are you doing the iteration, and then step 3 is output transformation, right? Which may or may not be there. Okay. Okay. So now let me explain this MD construction. Suppose that the compress function is mapping m plus t bits to m bits. Okay. T is obviously greater than or equal to 1. Suppose this is a collision resistant function. So actually I will show you that if compress function is collision resistant, the hash function is a collision resistant, So this is a very important. So basically we can do the security analysis of this construction. So as long as compress function is collision resistant, everything is fine, Okay. So compress function is m plus t inputs giving you m outputs. Okay. Now we will construct a collision resistant hash function. How do we construct this? H is from a set x to 0, 1 m bit output where x is union I is equal to m plus t plus 1 to infinity, something like this. Therefore, H takes any finite bit string of length more than, so H takes finite string of length at least m plus t plus 1 So that's the lower bound here, right? And creates a message digest of bit string of length m. Okay, because of this. So hash function. So if compress function is collision resistant, we would like to construct a collision resistant hash function, which is behaving like this. Okay, so I think I would like to show you one case when this is basically how to construct this. Okay, I think maybe we should do it next time, I guess. Okay, because it is a bit lengthy. Anyway, so we'll describe this construction in more details. How to construct a collision resistant hash function from okay collision resistant compress function. Anyway, so I think thank you. Today I'll stop at this point because it will not be I will not be able to cover it in this lecture, so I have to start afresh. Anyway, thank you. So if you have any questions, you can ask.